So we start off the first part of the chapter 2, actually the second part of chapter 2, with the real number line, something that we studied and we've kind of been talking about for a while. And this real number line is a topic of much study. So much, in fact, that there are entire courses in college built to studying just this thing. In fact, you could focus in on just the region between -1 and 1 and have an infinite number of numbers to work with. But we kind of back up a little bit and we look at the bigger picture, and we look at how we talk about numbers. So when we're talking about number systems, we're talking about things that themselves lend themselves to kind of specific areas of study. This means that you can limit yourself to just talking about certain kinds of numbers. Originally, when you first learned how to count, you counted with 1, 2, 3, 4, 5, and so on. And those numbers were given a specific name. Those numbers are actually called the counting numbers. And that's one name for them. Your book and what we're going to call them is another name. They're called the natural numbers, because they're numbers that we feel naturally occur. Now, that's a little bit of a misnomer, because so many numbers that we're going to study that aren't counting numbers do naturally occur. But they're the numbers that you can count on your hands. So I like to say this as count on your hands. Now, you can't count 11 on your hands, but you get the idea that you could have 11,000 of something and still a counting number. In fact, if I gave you the number 1,697,864,972, that is also a counting number. This is a counting number, or a natural number, because it's a whole number. It's positive. It's a number that you could, if you had that many hands, you could count that. We certainly have that many people in this world. We have more than that. So we give the symbol of an N, and we do this funky like double side thing with the N to describe the natural numbers. So that's the natural numbers, and they build up the first set of numbers that we're describing. Bigger than the natural numbers, and I kind of use the word bigger a little bit loosely because it's not really a bigger set, and we'll get to that much later in your studies about how this is the same size set as before. But the natural numbers are encompassed, or a subset of, the whole numbers. And the whole numbers are the same as the counting numbers, but we add a number, we include a number, I should say, that's a number that wasn't included. We include the number 0. 0, 1, 2, 3, 4, 5, and so on. We include the number 0 because that was an important discovery. The idea that we could have a number 0, that we could discover that we can use this to mean things. This was a huge area of controversy in ancient times, because they didn't feel that 0 was a number. Roman numerals did not use a 0. Roman numerals started with the number 1. And when you learn how to count with Roman numerals, 1, 2, 3, and so on, you don't actually have a 0 element. In fact, their 10 is just an X, their 100 is just a C, but you don't have Roman numerals that have an actual 0 in them. So Roman numerals did not have that. We use the symbol with a W with a funky side to talk about whole numbers. So that's whole numbers. Now, I'm going to kind of come back up here and say that the natural numbers, N, and I would never count off if you just put an N, but it's fun to put the double side thing. They're a subset of the whole numbers. And we're going to draw a picture in a little bit that kind of explains that. Every natural number, I'm going to actually include that in this, every natural number is also a whole number. That's an important distinction to know. Every natural number is also a whole number. So it can be part of more than one set. Then we move on to the next number set. We kind of have all these positive numbers. Well, another controversial topic was when the idea of integers occurred. Integers or integer numbers or integral numbers, if you want to kind of keep it going, you can call them integral numbers, they included the negatives. They were -3, -2, -1, 0, 1, 2, 3, and going on infinitely far in both directions. So if they go infinitely far in both directions, we have a few properties of this. We know that every whole number is also an integer. And integers are kind of the numbers that we very commonly express as what we think of as numbers. I would say this is the most common place we arrive at when we talk about things that we can actually quantify. Money is in integers for the most part, although if we talk about cents and fractions of numbers, fractions of money, then we aren't in integers anymore. But this is where you spend a lot of time adding and subtracting. You learn things like 2 minus 7 is equal to -5, and that's an operation that's contained completely within the integers. There is an operation that if we start to introduce that we can no longer be in integers, and that has to do with the idea of divide. I've said to freshmen especially that if we introduce division, we introduce one of the most important concepts, if not the most important concept of high school mathematics, and that is the ratio. So I'm going to put the word ratio down, but I'm going to make it its adjective form. Instead of ratio, I'm going to call it rational. That's the adjective form of the noun ratio. And a rational number is a ratio of integers. In other words, we take any integer, and divide by another integer. And we got to be really, really careful about that because we divide it by another integer. There's one integer we can never divide by, so we'll say another non-zero integer. And then we're okay. We've covered all the possibilities. So the integers, which I totally forgot to put the symbol for integer, the symbol is a z. We can't use an I, and it's a really cool reason why we can't use the I. That's coming later, much, much later. And for rational numbers, we're going to use the symbol Q because we can't use the R. We've already used the R. But a rational number, a formal definition of a rational number is it's an A over B where A and B are integers. So these are your fractions. These are your common fractions. These are your decimals. These are all the things that we think of as fractions and decimals with a few exceptions. First of all, the number 1/4 is an integer because it's 1 divided by 4. The number 10 is an integer because it's actually 10 over 1, and we just write that as 10. 0 is an integer because it's actually equal to 0 over 1. -5 is an integer. -5/6 is an integer. -11/2 is an integer. -172 111ths is an integer, although that's an integer that actually can't be simplified. So we have all these different possibilities that are integers. We have 7 over 9. We have 1/3. We have also the ones that's decimals, but they're a specific kind of decimal. They're decimals like this, 0.3 repeating. 0.3 repeating is the same as 1/3, so I could change that into an integer, or a ratio of integers. I could change the number 0.127 or 172, 172, 172, 172, etc. I can actually change that, and we'll learn a little bit later how to do that until 172 999ths, and that is a ratio of integers. Basically, any repeating decimal. Now it's funny because if I say any repeating decimal, I'm actually true. 0.4 is a repeating decimal. It's repeating because the part that's repeating is the zeros that follow. That's actually a repeating part of it. So any repeating decimal is what we call a rational number. Rational numbers, yes, it's such a specific case. It's such a special subtype of these. And what's important to note too about rational numbers, because I can put anything over 1, all whole numbers, and actually I'm going to say all integers, sorry, are rational numbers. And I'm going to zoom out a little bit and put a little box around the rational numbers. It takes a lot to explain what a rational number is. And if I look kind of back at the progression, I have natural numbers are a subset of the whole numbers. Whole numbers are a subset of the integers, and integers are a subset of the rational numbers. Diagramming this down here, if I have natural numbers are kind of their own thing, and they're contained within the whole numbers. Now, that's a lot just to include the number 0, but hey, it's just a visual. And those are contained within the integers. And that's contained within the rational. There's another kind of number that, simply put, is existing outside of this whole thing. It's over here, and it's not connected to these at all. If over on the left we have rational, then over on the right we have the opposite of rational, which we call irrational. Irrational numbers. And these are very, very tricky to understand, but we're going to do our best to kind of guide you through this. Irrational numbers are numbers that, simply put, cannot be written as a ratio of integers. Or what I'm going to say is cannot be written as one integer over another. So what I'm going to kind of show you here is, let's say that I have a bag of sand, and inside this bag of sand, this is a bag, and it's a bag of sand. That's a terrible bag. Let's draw a little bit of a better bag. There's a bag. That's just terrible. Okay, there's a bag. And we have an infinite number of rational numbers, and they're represented by infinitely small blue particles. Those are all the irrational numbers, and I could keep doing this forever, but they're infinitely small, so I can fit in as many as I want to in this bag. Well, these are the irrational numbers. It's actually the rest of the universe, because the universe is infinitely large, and there's infinitely many of these things. So if I exploded that bag and just basically did like a poosh and exploded that bag all throughout, so that now I have all these rational numbers combined, there'd be so many more, and I could do this for the end of time because I don't have enough time here. There'd be so many more irrational numbers that it'd be very, very hard to find the rational ones. I'm telling you this because the irrational numbers are so dense. They're numbers like 1.7278, 12150, 171. I am not doing this with any distinguishable pattern, and yet that's an irrational number. All of these are the irrational numbers. You guys all know one. You know 3.14159. I don't know the rest of it, but that's pi, and that is an irrational number. We're going to learn some other ones too, but numbers like radical 2 and radical 3 and radical 7 and radical 84 and anything that's not a perfect square root, those are ones. They are decimals with no pattern that never end. Think about that. Decimals with no pattern that never end. And you can see way up here how I drew the irrational numbers. I'm going to box this in, and look at how I drew the irrational numbers next to the rational. Irrational numbers are not rational. So they don't include any of those other kinds of numbers. They don't include integers. They don't include whole numbers. They don't include natural numbers. And the symbol for irrational numbers is a Q with a prime next to it. And we're going to put a funky Q. That's the symbol because it means not rational. If rational is a Q, Q prime means not rational. So let's show you kind of some classifications that we can do with numbers. I'm going to put a few examples down. Let's start with the number 81 fifths. 81 fifths is a ratio of integers, so it is rational. But the square root of 87 is not rational because I can't express that as a number divided by another number. Okay. That's kind of a little bit of a basic difference. We'll dip into more of this, but we also have a number that both of these numbers are a part of because no matter what you have, both of these can fit on this thing. 81 fifths is rational. Now, if I divide 81 by 5, I'm going to get, oh, we can do this in our heads. I'm going to get 1 and 16 and 1/5. Well, I could put that right here at 16 and 1/5, and I know where it is on the number line. Radical 87 that's between 9, which is radical 81, and 10, which is radical 100. It's between 9 and 10, so it would be probably somewhere in here, between 9 and 10. I know where it exists on the number line. I just don't know its exact decimal values. This number line, this thing is called the real number line. We give it a symbol of R. So what I'm going to kind of say is real numbers. Real numbers is every number on the number line. Or what I kind of say is they are either rational, which we have as a symbol of Q, or irrational, which has a symbol of Q prime. And we give real numbers the symbol that you've seen for all real numbers that are. That means that 81 fifths right up here is rational and it is real. And radical 87 is not rational, which means it is actually irrational, but it is also real. And if I go way back up here, way up to the top, natural numbers are part of the whole numbers, which are part of the integers, which are part of the rational numbers, which are part of the real numbers. And irrational numbers are also part of the real numbers. These two things kind of solidify the families that we've created. They're both parts of the real number. Every real number is either rational or irrational. So let's give some more examples. Let's say I have a number like 8.672, and let's say I have a number like the square root of 26, and then let's say I have a number like, I don't know, 10,001, and then the number is 0. And what we're going to do with these numbers is we're going to name all the number sets. We're going to do this with symbols because that's faster. So I'm going to start by saying, is 8.672 a natural number? No, it's not a counting number. It's also not a whole number, nor is it an integer because it actually has a decimal part. So then I look to see, is it decimal part, does it have repeating parts of it? Or is it ending? Well, it's repeating actually with the zeros that follow. So this is a decimal that could be changed into a fraction. That is a rational number, which means it's also a real number. These are the number sets to which it belongs. Number 4, radical 26 is not a perfect square root, so it is not a rational number. So I'm going to do a Q, but put a prime next to it. But it is a real number because all irrational numbers are also real numbers. 10,001, let's go to this one, number 5. Number 5 is a counting number. I can count that if I have 10,001 people. So that is a natural number, n. That is a whole number, w, that is an integer z, that is a rational number q, and it is a real number r. It is all of these, because if you're a natural number, you are part of all of those sets. Finally, the number 0. 0 is not a natural number, so that is a whole number. It is an integer, it is a rational number, and it is a real number. Let's do some more examples. Let's make these look tricky. Let's do the square root of 100 over the square root of 25. Then let's do 1.26 repeating. Then let's do the negative 1010. And then let's do this number. 1.821282017234. Okay. Well, the first one right here, that can actually simplify to 10 over 5, which is 2. 2 is a counting number, otherwise known as a natural number, a whole number, an integer, a rational number, and a real number. 1.26 repeating, well, it's repeating, so I could actually change that into a fraction if I wanted to, and since it's a fraction, that's a rational number and a real number. Number 9, I could change that. Well, that is an integer. It's a negative number, which means it's not natural, it's not whole, but it is an integer. Since it's an integer, if I look back up at the flow chart, integer to q to r. It's an integer, a rational number, and a real number. Rational, real. And finally, this thing has no discernible pattern. It would have to be irrational, but it also means it's a real number. Okay, I'm going to do one more little thing to show you something, and that has to do with the fact that these repeating numbers are in fact rational. This is from Mrs. Manton. I've never seen this proof, this style of proof. We'll do a different kind next semester. But here's a proof directly from Mrs. Manton that 1/3 is the same as 0.3 repeating. If I let n equal 0.333333, and so on, and I decided to subtract 10n, now 10n would be the same as sliding this decimal point right, so that would be 3.33333333 repeating. I get negative 9n on the left, and if I subtracted this, basically I'd get 0 minus 3, because each of these would cancel. This would cancel, this would cancel, this would go, that would go, and so I would get negative 3. That means n is equal to negative 3/9, or negative 3 over negative 9, which is 1/3. This is showing me that n equal to 0.3 repeating is the same as n equals 1/3. This is one way to show you that. Okay, that is part 1. You can stop for now, and we're going to get to part 2 here in a second.